Herkes burada abi. Of 10 kişi. Az.
Morning, good afternoon.
Hi, Antonio.
Hi.
Hi. How are you? Are good?
Good, good. And you?
Yeah, also.
Great.
Okay, so I think we could start. So, welcome everybody to this sixth talk of the Virtual Exchange Seminars in Quantum Mobile Networks. As usual, before moving to today's presentation, I would like to ask the audience if there is any questions regarding the previous presentation's content. As usual, for the students who need to receive the CTS or the credits for the course, I have added in the chat the link to the exercises to be solved before the deadline and the link to the evaluation sheet for today's talk. Also, for the students of the University of Bern who want to receive a final grade for this course, I also have added the link for registering on the UniBern's KSL portal for so that I have the chance of adding the final grade after the final talk. Okay, so if there is no questions from the audience, we can move on to today's talk, which is titled Gossip Protocols in Quantum Mobile Networks. The presenters are Rafieh Mosaheb from the University of Luxembourg and Ihsan Ufuk Dede from University of Bern, Switzerland. As usual, the presentation is roughly 30 minutes with some flexibility, and then the presentation will be followed by a rough 15 minutes question and answer session. As usual, you can ask either questions to the in the chat. You can leave it in the chat, and then I will pick them at the end of the talk, or you can ask your questions directly to the presenters at the end. Okay, so the first presenter might start the presentation.
Yes, thank you very much for the introduction, Antonio. So I will be starting with my portion of the presentation. That is more related to the papers that are more on the communication side. Also, my second paper is going to be more related to the quantum gossip protocols. The first one will be more rather about a temporal network where there is room for application in quantum networks as well. And then obviously I will pass the ball to Rafieh and she will continue with her part. So for my first paper, the motivation of the paper was to calculate a diameter of an opportunistic mobile network. To give a quick definition for both diameter of a network and what a opportunistic mobile network is. So basically, by calculating by the way we mean that we are calculating a route to from one node to another where there is 99% more than 99% of success rate. That's what they are aiming for in the paper. And in this kind of an environment where you have mobile network where all the time the connections between nodes and the contacts are changing, works have been done, but differently in this paper, what they are doing differently is they are introducing the temporal graphs. So they are also taking into consideration that the connection between two nodes, the path to there can also change while you're transacting the package. So that's also as a plus what they are considering differently from other papers. So yes, how they define a random temporal network in the paper is they propose this constant number lambda, which means the rate of contact of a single node with the other nodes per a certain time. And it can be two random networks, and this lambda is assumed to be constant for those nodes. And towards the end of the presentation, we will see that they also applied this in actual real mobile networks, and they were able to achieve a similar lambda, at least an average. So this is also kind of applicable and practical. So to be able to calculate this diameter that I have introduced at the beginning, like how many hops would you at maximum need to reach out to any other node in a temporal network, they consider two types of contacts. A contact is basically one node being able to communicate with the other and being in the distance or having somehow a connection with the other mobile node. So they have two definitions of contacts in that regard. The first one is the short contact. In the short contact, the definition that they give is it's a contact for a time slot. In the discrete time model, they have two time models that they consider in that regard, and it's a negligible time in the continuous time model, and then it doesn't exist for the second or the continuing time after that point. And for the long contact, there's contact for any number of edges in the given time slot again. So it's rather an interval where there's a constant contact with any number of edges in the network. Then for each node in the network, they try to estimate an expected number of paths, delay, and hop count for both short contact from short contact perspective and long contact perspective. So actually for these two models, what differs most importantly is that For the long contact, we can see that as the number of nodes in the network increases, also the paths that can be found between two randomly chosen nodes also increases. So that converges towards that. On the short contact, on the other hand, it actually again increases logarithmically, but not as efficient as the long contact. So it is rather hard to find paths between the randomly chosen two nodes in the short contact model. In reality, of course, again, in the tests that they do in the real mobile networks that we will see in a couple of slides, they are considering both cases because in a real mobile network, you cannot predict how the nodes are going to move, and also you cannot assume whether it's going to be a short contact or are you going to have two nodes always being able to communicate with each other for a long time. So in the actual experimentation, they we will see how this is viewed. And coming on to the diameter of a network, so the outcomes and the definitions that they give is in the paper, it is shown that a source destination pair admits on average many forwarding paths using a small number of hops and over short number of time slots. And on the other hand, the hop number of these paths seem rather insensitive to changes in the contact rate, lambda, with the only exception of the long contact case around the value of lambda equals 1. So regardless of the lambda's value, the hop count doesn't really get affected. So as long as it is more than one for the most of it. And looking at these results, one may compute the diameter of a network. So we're coming to the definition of a diameter of a network at that point, using the path with an optimal delay and deduce the temporal network generally have a small diameter for almost any contact gate. So they are basically from the fact that regardless of having small number of contacts per minute or more contacts per minute, they can calculate this general diameter that you can have for a certain number of nodes within a network, regardless of their contact rate. So that's how they define the diameter of a network, and that's what they aim to calculate. And yeah, ultimately the definition for that is the diameter of a network is an upper bound on the number of intermediate hops needed to find at least one path between two nodes. And we are saying that if as long as lambda is greater than 1, that's not being affected that much. And the real life experimentations that I've just mentioned are given in here. So they have different mobile networks with different properties where they have plotted the communication between two nodes, like being able to find it or not. And in any of the networks, you're like the properties are, by the way, like durations, granularity, number of experimental devices, number of internal contacts, rate of contact, number of external devices, number of external contacts, and rate of contact, including the external devices and only internal devices. The differences is between the two rate of contact properties. And there, again, on the right, for all of the data sets, for all of the networks that are given, you can see how many delay have occurred between the communication and being able to find a path to any given node in the network. So so for the first paper, only the conclusion that they arrive at is that they have proved the small world effect. So for any given number of nodes in a network, you can always find a path to one of the nodes wherever that is at any given time, depending on some variables that are mentioned, obviously. But yeah, that can be found. So they prove that. And also another thing that, again, coming out of this is that that they claim they actually arrive at is that real life human networks, mobile networks, they vary between 3-6 hops as well. So this is also very similar to that case, the conclusion that they arrive at in here. So yeah, that is about, again, as I mentioned, rather about the mobile network where there is probabilistic changes in the network. So also probabilistic changes between the communication of two nodes. This I've seen as a place where quantum also can be applied to. But again, that will be rather introduced more in detail in the Rafieh's part in a very similar scenario. Coming on to the second paper, the second paper is about arriving at consensus in a quantum network, a symmetric consensus with gossip interactions. So basically, what they are trying to do is they are trying examining how symmetric consensus in a quantum network can be achieved, and yeah, also there are some again, as quantum is involved, probabilistic scenarios in that regard. So they're also trying to preserve the expectation of any permutation invariant observable. And in the paper, they define, obviously, first the classical consensus. And when we talk about classical consensus and symmetric consensus, we are talking about all of the nodes being able to arrive at a basically be able to arrive at a certain truth, we can say, or certain data, and all of them having all of them agree in that. And when you say symmetric, it's basically that they're all contributing equally to that consensus. So with the quantum network, also we're going to be they have also been looking to achieve a symmetric consensus where all of the nodes, all of the quantum nodes, are contributing equally to the consensus. Again, the differences that this brings doing this like in a classical consensus, it's pretty straightforward. You just, I mean, there are obviously complex algorithms, but it is more deterministic, I would say, to arrive at a consensus. But on a quantum network, it's rather probabilistic. And um, here, I should have actually said when is what is consensus in quantum network. Also, that's a question that they raise, and also in the upcoming slides, I will be talking about the definitions that they give for consensus in a quantum network. So they actually examine it in three main headers. They actually say that there are three different types of consensus that can be arrived in a quantum network. First one is the uh, tau expectation consensus. So there, the definition that they give is the agents are said to be in consensus if they converge to a state in which the expectation of a given observable tau is the same for all agents. This can be expressed mathematically in this formula, and where P is the density operator representing the state of quantum network, and tau I is the observable associated with the ith agent. So already here we can preserve some probabilistic nature and the type of consensus that we're trying to arrive in the quantum network. And the second type of consensus that you can arrive at in a quantum network is the reduced state consensus. So in that case, the agents are said to be in consensus if their reduced states are the same. This can be, again, expressed with this formula right here. And the equalities, the member, like the all the sides of the equalities denote the partial trace over the subsystems respectively. And then finally, we have the very similar consensus case that we have in the classical consensus, the classical symmetric consensus. That's where the state, so in that case, the agents are said to be in consensus if they converge to a state that is invariant under any permutations of the subsystem. And to arrive at these consensus, they also propose using a gossip algorithm. So they are presenting a gossip algorithm that asymptotically prepares symmetric state consensus states while preserving the expectation of any permutation invariant observable. So this is actually the ultimate goal of the paper. Out of the three types of consensus that you can arrive at in a quantum network, the one that we're trying to arrive at is a symmetric consensus uh, uh, where there's a consensus while also preserving the expectation of any permutation invariant observable. And the algorithm that they introduce is based on a fully quantum implementation of a gossip type interactions. The gossip algorithms are all actually Rafieh's, again in Rafieh's part, she dives more in depth to that, the gossip algorithm part in particular. Here they are leveraging the gossip algorithms to arrive at consensus, particularly. And that is done where unitary transformations are used to implement the swapping of two neighboring subsystems states. That's also the core idea of gossip algorithms, and this is what it is leveraging. Two nodes that can communicate with each other are sharing their states, subsystem states, and that's eventually how all of the nodes arrive can arrive at a consensus. The algorithm is proven to converge to symmetric state consensus with probability 1. So if you actually try to implement this consensus in a quantum network with using gossip algorithm, they in the paper they prove that it will 100% eventually arrive at consensus, and the convergence is exponential when the edges of connected graph are selected in a cyclic way. And also they introduce some applications for that sake. But yes, I will have to quickly mention these and then move on to the second half of our presentation. But yeah, the applications that they introduce are estimation of global variable from a subsample, purifying and cooling of a sample by local feedback actions, estimating the size of a sample. And yeah, here again, the most important part to mention, I would say, uh, regarding the conclusion that the paper arrives at, it proposes an analysis of quantum gossip type algorithm that asymptotically prepares symmetric state consensus states while preserving the expectation of any permutation invariant observable. And they actually, with their model, they succeed in this particular uh, goal that they have initially, that with their motivation. And the further questions that they raise are that there can be it can be so there can be a link between, again, different consensus states and entangled states, and to determine if and under which conditions it is possible to achieve this type of consensus with a distributed algorithm rather than a symmetric one. And yeah, they also propose that uh, dynamics of continuous time dynamics can also be uh, leveraged for this type of consensus. And yes, that's it's for my part. Thank you.
Okay, thank you, Ihsan. So shall I share mine?
Yes.
If you stop sharing, yes, thank you.
No problem.
So can you see my screen, full screen?
I think we can see the presenter view. Maybe you want to switch the monitors because we can see, for example, the
Okay, so
and so.
And now it doesn't work?
Yes, now we can see the whole PowerPoint panel.
Okay, so it's in full screen, right?
Yeah, if you click full screen or like the presentation button, maybe it should work. You can try.
If you can, I can also share and then just move when you say.
I hope that I can somehow fix it soon.
Yeah.
Okay.
Do you have two screens? Try to share the screen that is showing the PowerPoint. Use the
Yes,
Zoom tool to change it.
Yes, I tried to share the other one, but for some reason it doesn't work. Okay.
And now start your PowerPoint presentation.
So now you see?
Yes.
Okay, perfect. So sorry for the delay. Hello, everyone. My name is Rafieh, and I'm going to give the second part of our talk regarding gossip protocols in quantum mobile networks. So what do we cover here? There are three papers that I'm going to talk about. The first paper mostly investigates the question of how the information distribution in quantum networks can be sped up using gossiping. The second paper investigates how we can model quantum gossip networks using random graph theory and what are the statistic performance of this approach. And the last paper investigates the question of accelerating classical gossip algorithms using local click operations. And you can see these three references here. So regarding the first one, gossip algorithms in quantum networks. So first, what does gossip algorithm mean in general? Actually, a gossip algorithm is inspired by a natural way of rumor spreading in social networks. I mean, the terminology that you all have in mind. This describes protocols for unreliable information dissemination in natural networks which have unknown structure. And the goal in this paper is to first prove that any quantum network can be updated to an optimal configuration using local operations and classical communications. We are going to see this term several times. So what does it mean? It means that a quantum state is shared between two nodes, and each node can apply quantum operation on its own shared part. But they cannot transfer or communicate any quantum information, just classical information, for example, the result of the measurement or so on can be conveyed. So this means local operation and classical communication. The next goal is to analyze the performance of gossip algorithms on quantum networks. And the main result in this paper is that this indeed can be speed up the quantum information dissemination, and in some cases this speed up can be exponential. There are some background information needed in this paper that I'm going to quickly explain. The first one is that we know that real-world networks have some non-trivial structure features, and this means that it's practically impossible to completely simulate their dynamics. And the second point is that it is hard to design optimal protocols for information dissemination in these complex networks. The next point is that quantum networks are also complex, so they are the same. And the last thing is that using this local operation and classical communication approach, we can change the connectivity of a given quantum network and simulate the complex entanglement graphs on a simple underlying quantum graph. After that, there are some notations that we have on this slide. The first thing is that in discrete random walk, we have a transition matrix that we show by P, which entries Pij. It means that each node I and j, they are connected with this probability Pij. But here the assumption is that there is no constraint on the direction of the information dissemination. So it means that the graphs that we consider are undirected and the transition matrix is symmetric. Then we have 4 auxiliary functions. The first one is the conductance phi p. This means this is modeling the information dissemination capacity of a graph. So you don't see any notation for the graph, but this transition matrix is going to suppose is supposed to show the graph. And this capacity of information dissemination is modeled with this formula is the minimum over the sum of this transition probability Pij for the nodes I in a set S and the J's in the complement set. There is an assumption on the size of this S to be less than half of to contain less than half of the total number of nodes. And then we have the K conductance formula. The only difference is that we restrict the size of the set S with K instead of n half. And of course, K is less than or equal to n half, and we call it K conductance. Then we have the mean conductance, which is the sum over K of K over this K conductance formula that we have here. And the last function is the epsilon dissemination time, T epsilon, which is one of the most important functions here in this paper. And it means that the time that all the nodes have the information with a high probability, with probability 1 minus epsilon. To have a better sense of these functions, there are 2 examples. The first one is about a complete graph. So here the complete graph has 8 nodes, but it can have any n number of nodes. The probability Pij in a complete graph is 1 over n. With this probability, we move to the other nodes. So considering this transition probability, if you substitute it in this formula, we can see that the capacity of the information dissemination is big O of 1. If we substitute it in the formula for the mean conductance, we can see that the mean conductance for the complete graph is order of n squared time logarithm of n. We also have the same formula for a ring graph, as they call it. And for the ring graph, the probability PII, it means that when the node J is equal, I mean, it's the same node, it's 1/2. And for J, which is not equal to I, the probability is 1/4. By substituting this transition probability, we can see that the conductance phi p is order of 1 over n, and the mean conductance is order of n cubed. And if we compare this complete graph and the ring graph, it's what we expected, because we expect the complete graph to have a better capacity in terms of disseminating the information. So next, the goal is to estimate this epsilon dissemination time with the conductance function. So they differentiate 2 cases, the single piece dissemination and the multi-piece dissemination. In the first one, there is a single node that wants to transfer or disseminate the information. So let this node be V at time 0. Then T1 of epsilon 1 is used for the single piece. Is equal to the supremum of infimum of this set for the time t, where the probability, the conditional probability is starting from a node V and achieving a set ST, which is not equal to all the nodes V, is less than epsilon. Then there is a theorem in this paper that it actually finds an upper bound on this T1 of epsilon, which is order of logarithm of n plus logarithm of epsilon inverse over the conductance of the graph, the capacity of the graph. And to have a better sense of this formula, we can just substitute the parameters for complete graph and for the ring graph. So for the first one, for the complete graph, this T1c of epsilon is order of logarithm of n, because for complete graph, this phi p is order of 1. And then we have a sum here that they somehow I mean, this is the bigger term, so we can see that it's order of logarithm of n. And for the ring graph, this phi p is 1 over n. So at the end, we have n logarithm of n. And then for the multi-piece dissemination, at time t, we have a set m of m1 to mn, and each node wants to convey its own message to the other nodes. Then the definition for Tm of epsilon is infimum over the time t, such that starting with message mi for the node I, the union of these SIs is not containing the whole messages. The probability is less than epsilon. Then the theorem finds upper bound over this Tm of epsilon, which is the mean conductance pi times logarithm of epsilon and inverse over n. Then again, by substituting the values that we know for the complete graph and for the ring graph, we achieve this to upper bound. For the complete graph is order of n logarithm squared of n, and for the ring graph is order of n squared logarithm of n. So we can see that it takes more time to disseminate information in the ring graph than complete graph. Then next we have gossip algorithms in quantum networks. So the quantum advantage is that in the compared to the classical case, if we want to change the conductance, then we need some additional physical connections between the vertices. But in the quantum case, we can use like teleportation and entanglement. And to update the quantum network with entangled edge, we can do this to advance the quantum to advance the gossip algorithm. And there are two characteristics. The first one is local characteristic, which is the average degree of the graph. We show it by k hat, which is 2 times e over v. And then we have a global characteristic, which is the average path length, which we formalize it by LG. And here d of v and vi and vj is the shortest path between two vertices. So what we want to do here is that we want to prove that we can update any connected graph to a complete graph using a polynomial number of local operation and classical communication. So what we are going to do is that we need to find an upper bound. So we need to find the graph which has the most restriction. This graph has to have the lowest average degree and the highest average path length. So for this goal, it's enough to use a ring graph. For example, ring graph has an average degree of 2, which is the minimum. So here they also differentiate between two cases. Again, the single piece dissemination and the multi-piece dissemination. So in the single piece dissemination, what happens is that for the ring graph, we need to choose the longest non-local entanglement edge by n⁻⁻1 entanglement swappings. And then the total number of non-local edges are n-1 times n⁻⁻1. And then we need to repeat this for each node, which gives us the total number of entanglement swapping of order of n cubed. And this is indeed the upper bound on LOCC in any quantum graph, because the ring graph is the one with the highest restriction. And then for the ring, if you assume that the number of nodes are 2 to the power of k, we know that the fastest classical dissemination needs 2 to the power of k minus 1 steps. But in the updated network, the number of steps are k. And at the same time, we just need order of n cubed or a polynomial number of LOCC. And then for the multi-piece dissemination, the assumption is that we have a set of messages psi1 to psi n, which are like qubits. And the point is that here each edge has to be used has to be used n times instead of 1 time compared to the single piece dissemination, and it means that we need to have generalized edge. We need to have an n times copy of the edges, which gives us total number of local operation of order of n to the power of 4. And at the end, this update of the ring graph to the complete graph can improve the time dissemination of the ring graph to a complete graph. So it's improving this number. Then regarding the second paper is about the quantum complex networks. First of all, what are complex networks? They are like chemical reactions in a cell, spreading of disease in population, or communications using internet or etc., which have non-trivial topology. The goal in this paper is to find applications of quantum mechanics in complete networks. And what they are doing is that they introduce a simple model of complex quantum networks. The main result in this paper is that if we have a network of n nodes, and if the entanglement between pair of the nodes scales as n to the power of -2, then they prove that any quantum subgraph can be generated using this LOCC. The background information here is that in general, to model complex networks, in the literature, they are using random graphs. The simplest case is to consider this probability Pij some constant P, and then we show the graph by G of n and P. Then here we need to talk about typical graphs, but before that we need to see the evolution process of a classical random graph. So first we start with isolated nodes, and then we randomly add edges by increasing this probability in order to at the end have a complete graph and have a probability P equal to 1. So the important question here is that at what stage of this evolution a particular probability of the graph is likely to rise. First, we need to think about a definition, which is a probability space. It means that in this space we have all the graphs with a given set of n labeled vertices and m edges, and each such graph is assigned the same probability, as I mentioned before. And then we are interested in the properties of this space when n tends to infinity. And then the typical element of this space has some specific property Q when the probability that a random graph on this n vertices has this Q tends to 1 as n is tending to infinity. Then according to this reference, random graphs of Balobash, it's mentioned that for many properties, there is a threshold or a critical probability PC of n, such that for each probability which is higher than or equal to this probability, almost every typical graph has the property. To see an example to make this more clear, the critical probability for appearance of a given subgraph F with n nodes and L edges in a typical random graph is C times n to the power of -n over L. And this is the proof can be found in this reference. Here for different subgraphs that you can see here, for example, for this one, which is an edge or a complete graph on 2 nodes, this -n over L, or as they call the exponent Z, is -2. And as you can see, when we increase or somehow decrease this exponent, we can see that at first these trees start to appear, and then when this exponent arrives at -1, then we see that cycles appear, and at the end we have a complete graph. So this probability pi is somehow p is proportional to n to the power of z. And then for the quantum networks, what happens is that instead of this probability Pijs, we substitute them with density matrices with the quantum state rho ij. And we assume that each pair is identically connected, so it's a constant rho. And the exact definition for this rho in this paper is this pure state. And the goal here is that, so for example, here we have five nodes, and each node contains 4 qubits. So these qubits are sharing this entangled state with the rest of the nodes in this graph, and the goal is that we want a maximally entangled state. So here is not equality, it's proportion, because the probability is not 1, as you see, but the success probability here is P for achieving Ket11, which means that we can have a link between 2 nodes if we achieve this maximally entangled states. And here the probability P of adding these links is 0.25. And then the corresponding graph is G of N and P. So here we have an example of how we can obtain a GHZ, a state of 3 dimension and 4 qubit when Z is equal to -2, as we can see here. So the steps are as following. For each of the nodes, we need to apply in complement measurement PM. What are these PM? It means that we want to measure exactly M Ket1s, or in the other way, it means that we want exactly M links which are Ket11. And for each of these measurements, we either have 0 or 1, and as n tends to infinity, according to discrete math of Balobash, we know that this probability tends to 0. And then in this paper, they prove that if you consider the probability P to be 2 times C times n to the power of -2 for C, which is equal to 4, then there are in average C nodes that have exactly 1 qubit in a state 1. And this means that at the end, we achieve this graph KC. And this is somehow the perfect matching for complete graph K4, as you can see. And when they relabel it, it's Ket11, Ket11 plus Ket22, Ket22, and plus Ket33, Ket33. And the main result in this paper is that as n tends to infinity, and P is n to the power of -2, then we can obtain a quantum state with a structure of any finite subgraph with unit probability. It means that if this subgraph is F with n nodes and L edges, then we can have this state F. So as I see, I took a lot of time, so I can see that there's no time for the last paper. So I don't know whether I can continue or...
If you want, you can present it relatively quickly. Yeah, we can maybe shorten a little bit the question and answer.
Okay, so I try to explain quickly. So the last paper is about quantum clique gossiping. Cliques are a complete subgraphs in a graph, and the goal here is to use local clique operations to accelerate the classical gossip algorithms. The main result in this paper is that using large quantum cliques does not necessarily increase the speed of the network as we might think it does, and the quantum network dynamic is not entirely decided by the classical topology. So here what is important is that the performance metric of distributed algorithms are based on the rate of convergence, but the problem in improving this rate of convergence is some combinatorial obstacles for optimizing the weight of these links. What is the solution? The solution in this paper is to use some microstructures such as cliques. So what happens here is that we have an open network that it contains, as you see with these dashed lines, 4 local, 4 closed networks, and each node contains a single qubit. So here the graphs, they have edges, and each edge here is a generalized edge. So this is an edge between 3 nodes instead of 2. Then we have a set of permutations that we show them by P, and then we associate to each edge a permutation pi I. So here, for example, if we have 4 nodes, then the permutation maps the vertex 4 to itself. And then we can induce the quantum permutation operator U phi, as you can see here. So U phi applied on this tensor product of the states is psi of this permutation pi applied on the indices. And then there is the definition for the deterministic quantum clique gossiping. So here the density operation of this network in time t+1 has a relation with rho of t, as you can see here. So there is a function sigma that maps positive number z to E1 to EC, and then it picks one of them at random according to the definition of, not at random according to the definition of psi. And then this is the formula for deterministic quantum clique. And in case that each EI has size 2, then we have the standard quantum gossiping formula. And then there are 4 theorems. Briefly, these theorems, the first one is about the convergence rate of this quantum clique gossiping. They prove that the reduced state consensus in this network is, as t tends to infinity, is this average, and it has to satisfy 2 relations. First is on the union of these edges, which has to be the whole vertices, and it has to have the maximum connectivity, and then the network density operator that it satisfies this relation for the definition of S of E. Then in case that K and N, they have a specific relation, it means that actually N is divisible by K, then there is some time T, actually some time T that they have the same formula compared to the first theorem. And then here in the third theorem, the assumption is that the edges are K-regular. In this case, we can have like this convergence, this formula that you can see here. And then for the network, they have this convergence formula, as you can see here. So they differentiate 2 cases when K is even and when K is odd. They have these 2 formulas. So a factor of 2 appears here. And then they have this example for the reduced state convergence and for the network density convergence. And as you can see here, there is a relation that as K increases, the convergence also increases faster. But here there is no linear relation for the network density convergence. So this concludes my talk, and thank you for listening.
Okay, thank you for your presentation. Also very rich, very full of content. Is probably would have needed a couple of talks to cover all of this.
Yes,
we can open now the questions, so we can start taking it from the audience. Is there any questions from the audience? Yes.
Yes, maybe I will have a question for Rafieh. So for the first paper you presented, so I didn't really understood this update graph. So I think on slide 21.
Which one?
So in slide 20, your slide 21. So there are 2 graphs, and one is updated from, there's a circle graph and then a complete one. So
yes,
this,
actually. Yeah, the goal is that we first start with the ring graph. As I said, the ring graph has the more restriction among the other graph because it has the lowest average degree and the highest average path length. So if you want to send an information to the other node, the longest path is like the one which is here. I mean, you need to traverse half of the vertices. So that's why they start with this ring graph and they try to update it to a complete graph.
Exactly. And how maybe that's how the updates work.
So for the update is that there are some nodes that they are not connected together in this ring graph, and the number of these nodes is like I mean the number of edges that they're not connected is n⁻⁻1. So we need this number of entanglements to connect these two vertices together.
Okay, so which means there is some entanglement in the ring graph, and this is used then to connect the nodes to build those new connections. Or
yes, the ones that they are not connected already in the ring graph.
Okay. Thank you.
Yes, more questions. Yes, Neville.
Hello, thank you for your presentation, first of all. And my question is, did you find anything? I mean, I'm not sure if it's in the papers you reviewed, but just in general, did you find anything about like media access control and gossip learning? Because I think it could kind of have some use for media access control, or like who gets access to the channel at what point.
So I don't know whether this question is for me or for both of us, but in the papers that I reviewed, there are mostly no applications. So what they do is that they assume that there is a complex network and they try to model it and they try to make it better in terms of the convergence rate and so on. But they don't mention any specific applications, at least in the papers that I reviewed.
Okay, thank you.
Yes, more questions? Okay, maybe I can ask one, maybe to Ufuk. So you mentioned the concept of diameter of a network, and also you mentioned two different ways in which the expectation could diverge to 0 and to infinity according to the to some threshold. Can you really explain this really detail more deeply?
Yeah, sure. So the two ways of measuring that expectation is coming. So the first one is the short contact, where you're assuming that the contact that is being made by any of the nodes that is in the range of that particular node exists for a given time t only. For the continuous time, it's a negligible amount, and for the discrete time, it's for that particular time only that contact happens. That's
in short contact, how many links does the exchange take place?
There's a constant that they determine, the number of contacts that can happen per time slot, the lambda. So that's the answer to that is lambda, and that depends on the network itself, the properties of the network.
Whereas on the long contact assumption, what is the difference? Is that any element of the connected component can communicate, or what?
Yes, exactly. In the long contact version, it's about any node that it can contact, and it's not for a given time slot only. It's for a time interval rather.
And then you show that this is determined by a condition that happens or not, which is the 1/tau greater or smaller than gamma, the logarithm of lambda plus h of gamma. So I want you to describe what is tau, what is gamma, what is lambda, and what's a function h. So just to know exactly, precisely, what is this threshold.
So the precise part that I know that's that's most importantly is the lambda. So the amount of contacts that is assumed as a constant, or already exists as a property in a network. So the lambda is the most important number that affects that in that case. And I'm not sure about what the so there are actually two plots that I thought I added in the slides, but I actually missed them. So in those graphs, you can see much clearly how in both models the number of contacts is either converging to a certain amount or it is basically going down, depending on whether if it's got short contact, long contact, and lambda.
What about this tau and gamma? Do you recall what they change in the system?
Not very precisely, to be honest. Not very precisely, but as I said, in the plotted graphs, lambda and the time, that they like plot three graphs in two different axes. In the one, it's for the short contact, and the second one is the long contact. And depending on lambda, you see where the diameter converges.
Okay, then maybe one question for Rafieh. Okay, first of all, is there any other question from the audience? We can pick one more. Okay, so if there is no other question, then I can ask one. So just let me go to the slide 1 second. Yeah, it's slide 25. Yes, here there is a couple of aspects. So here you show the evolution process of a classical random graph with 10 nodes. So here you show 3 samples with different p. And then you say that there is an evolution in which you gradually add an edge to the graph. So, okay, so these are two very different things. You have one graph process in which you select a certain probability, and then you gradually add an edge. So this is to build one sample of these graphs. And then you have another one, which is simply selecting P, and each edge can be added to the graph with a certain probability P. So which one exactly do you mean in your explanation?
So what is happening, as I understand from the paper, is that we are adding edges and at the same time increasing the probability. So we are increasing the probability of adding an edge between the vertices. So we start with an isolated graph, nothing is connected to anything, and then the probability is P equal to 0.1. We add some edges according to this probability, and we are increasing it, and then we add more edges according to that probability, and then when we achieve the complete graph, the probability is already 1. It means that everything is connected together.
Yes, yeah, okay. I mean, what I wanted to hear is that there is some like a duality between two models of random graph.
I mean, this is not two model. Actually, this is one model. So this is one evolution process.
Yeah, in a certain distribution of graphs, you can parameterize in two ways, either with NM, which is number of nodes, and M number of edges, or N and P, which is the probability. So the certain graph, you can either characterize by fixing the number of edges or the probability of an edge belonging to the network. Okay, but then the actual question, so coming from this, is this critical probability for the appearance of a subgraph. So you have a subgraph NL, right, where small n and small l represent the number of nodes and the number of edges. So the appearance of this subgraph Fn has a certain probability, which is C n to the minus n divided L. So could you specify better what is C and I mean somehow
Yes.
more details on this threshold?
Yes, sure. Actually, C is a constant which is not related to n, so it's just a constant. Yeah, in this subgraph f of n, the assumption is that it has a small n number of nodes, and this a small n is smaller than capital N, which is for the original graph, and then it has some specific L number of nodes. So this is the formula in general, and then what is important here is the exponent of capital N, which is minus n over L. So this is what's important, and we can see that when a specific graphs start arising, when we are somehow increasing this number.
Mm-hmm. Okay, that's quite clear. So, do we have any further question from the audience? Okay, so from the presentations is it today, so we can thank the speakers. So before saying goodbye, there is an aspect that we have to do, which is the course evaluation. So I will share now a slide with a QR code, so the students at the University of Bern or anybody who has attended the course can give an opinion if you like the course, or what you disliked, what you liked most, what you want to see again, or what you would like to see less in a potential future edition of this course. So let me share it. So you should be able to see it now. So here you can either take the you can take a photo of the QR code, and you can do it on your phone, or you can also access the link that I'm also gonna add in the chat. So you can decide to do it now, or anyway, should be done before the 22nd of May. So let me share it in the chat as well. Oops, little problem, just a second. Yeah. Okay, so for today, this is all. So we will meet next Friday with group 7. Is anybody from group 7 here?
I'm here, Professor.
Okay, well, thanks for Professor, but not yet. Hopefully soon, but not yet. The title of the following talk would be Age of Information in QMNs, and have the people from this group had the chance of interacting or already starting preparing the presentation? Did you face any collaboration problem that we can solve now?
We talked and we defined the topics. Now we are finishing the presentation. I think we will have a more complex. Sorry for the noise, but we are going to present it next week.
Okay, so I see the state is progressing, so I'm happy. Okay, great. So if there is nothing else from your side, then we can say goodbye, and I'll see you next week. Thank you, everybody, for attending.
Thank you. Goodbye.
Thank you. Bye.
Bye.
Thank you. Goodbye.
Bye.
Bye.